Hello, my name is Sarel Cohen, and in this talk, I will present distance sensitivity oracles with subcubic preprocessing time and fast query time. This is a joint work with Shiri Chechik. So what are distance sensitivity oracles? Given a graph G, and in this work, we assume that G is a directed graph with integer edge weights in the range -m to m, we want to preprocess it into a data structure such that given queries of the form a vertex S, a vertex T, and either an edge E or a vertex V, we want to compute and return the distance from S to T in the graph G minus E or G minus V. We describe previous results of distance sensitivity oracles for the case of a single edge or vertex failure. Demetrescu et al. Presented a distance sensitivity oracle whose space is O of n square log n, it has constant query time, and its preprocessing time is O of m n square. Bernstein and Karger improved the preprocessing time in SODA 2008 and then in STOCK 2009 to O tilde of mn, keeping the space and query time the same. This is near optimal due to the conditional lower bound of combinatorial all pairs shortest paths. An interesting question is whether one can develop a distance sensitivity oracle with subcubic preprocessing time using fast matrix multiplication. Wayman and Euster presented in Fox 2010 a distance sensitivity oracle for directed graphs with small integer weights in the range -m to m, whose preprocessing time is subcubic O tilde of m n to the power of omega plus 1 minus alpha, where alpha is a parameter between 0 to 1, and omega is the matrix multiplication exponent. Their query time is subquadratic O tilde of n to the power of 1 plus alpha. An interesting following question is whether one can develop a distance sensitivity oracle with subcubic preprocessing time and sublinear query time. Grandoni and Vasilevska-Williams presented in Fox 2012 a distance sensitivity oracle with subcubic preprocessing time and sublinear query time for omega that equals to 2.373, and for a good choice of the parameter alpha, the preprocessing time is O tilde of mn to the power of 2.873, and the query time is O tilde of n to the power of 0.7. An interesting following question is whether one can develop a distance sensitivity oracle with subcubic preprocessing time and polylogarithmic query time. In this paper, we answer this question affirmatively by presenting a distance sensitivity oracle with the same subcubic preprocessing time of O tilde m n to the power of 2.873 for omega that equals to 2.373 and polylogarithmic query time. For simplicity of presentation, we will assume that all shortest paths are unique and that edge weights are positive integers in the range 1 to m. In the paper, we remove these assumptions. We will use the following notations. For a pair of vertices, S and T, we denote by PST the shortest path from S to T. For an edge E along the shortest path PST, we denote by PSTE, the replacement path for the edge E, which is the shortest S to T path that avoids the edge E. Without loss of generality, we may assume that the replacement path contains a common prefix with the shortest path, a disjoint detour, and a common suffix with the shortest path. We consider 4 cases for a query STE. Case 1 is when there exists a short replacement path containing at most 3R edges for a parameter R to be set later on in order to minimize the preprocessing time. Case 2 is when there exists a replacement path which either has a long prefix of at least R edges or a long suffix containing at least R edges. Case 3 is when the edge E is among the first or last R edges of the shortest path, PST. Case 4, which we also call the R-critical case, contains all the remaining queries. That is, all the queries that do not belong to either case 1, either case 2, or case 3, and we call these queries R-critical queries. Cases 1 to 3 are easy to handle and solve using prior work. Case 4 is the most technically difficult part of our paper. We first describe how we handle cases 1 to 3, and then we outline how we handle case 4. To handle case 1, when the replacement path contains at most 3 R edges, we use the distance sensitivity oracle of Wayman and Euster from Fox 2010. Its preprocessing time is O tilde of R times running all pairs shortest paths, which is subcubic for small enough R. Assuming that the replacement path contains at most 3 R edges, then its query time is fast, O tilde of 1. In the remaining of the cases, we assume that the replacement path contains at least 3 R edges. To handle case 2, where the prefix or the suffix contain at least R edges, we first sample a subset B of vertices, where every vertex is sampled with probability C log n over R for large enough constant C. With high probability, the size of B is O tilde of n over R. Also, for every pair of vertices, S and T, we find and store the first sampled vertex along the shortest path, PST, which we denote by VS. And we also find and store the last sampled vertex along the shortest path, PST, which we denote by VT. For every vertex V in B, we run the SSRP, Single Source Replacement Paths algorithm of Grandoni and Vasilevska-Williams from Fox 2012, which computes all the replacement paths for the single source V. Or more formally, it computes the distances dVTE for every vertex T and for every edge E along the shortest path from V to T. If we run the SSRP algorithm on the graph G with reversed edge directions, then it also computes the distances dsVE for every vertex S and for every edge E in the shortest path from S to V. The runtime of the SSRP algorithm is O tilde of Mn omega. So if we run the SSRP algorithm for every vertex V in B, then it takes with high probability O tilde of n over R, which is the size of B, times Mn omega, which is the runtime of a single instance of the SSRP algorithm. In order to find the distance dSTE for a query STE that belongs to case 2, we observe that with high probability, either the vertex VS is contained in the prefix part of the replacement path. This happens with high probability when the prefix contains at least R edges. Or the vertex VT is contained with high probability in the suffix part. And this happens with high probability when the suffix contains at least R edges. Therefore, to compute the distance dSTE, we can take the minimum of the length of a replacement path that passes through VS or the length of a replacement path that passes through VT. The length of a replacement path that passes through VS is dsVSE plus dvSTE, and the length of a replacement path that passes through VT is dsVTE plus dvTTE. And we know these distances as we computed the SSRP algorithm with the source vertex VS and with the source vertex Vt. Therefore, during query time, taking the minimum of these two distances takes constant time. To handle case 3, where E is among the first or last R edges of the shortest path PST, we want to pre-compute all the answers to all of the queries that belong to case 3. We will use the distance sensitivity oracle of Grandoni and Vasilevska-Williams from Fox 2012 in order to answer all the queries that belong to case 3. Given a parameter x, their preprocessing time is O tilde of mn omega times x to the power of 4 minus omega plus squared n, and its query time is O tilde of n over x. There are O of n square r queries STE that belongs to case 3. To see that, there are n vertices S, n vertices T, and at most 2 R edges E, which are among the first or last R edges of the shortest path PST. Each such query is answered in time O tilde of n over x. Therefore, recomputing all the answers to all of these queries take O tilde of n to the 3 R over x time, which is subcubic when R is significantly smaller than x. Then, during query time, given a query STE that belongs to case 3, we simply restore the answer that we already pre-computed and return it in constant time. We are left with case 4, the R critical case, which contains all the queries that do not belong to case 1, and therefore the replacement path contains at least 3 R edges. Queries that do not belong to case 2, and therefore the prefix and suffix contain less than R edges, and queries that do not belong to case 3, and therefore the edge E is not among the first or last R edges of PST. We denote by PRST the subpath of PST excluding its first and last R edges, which is this middle part, middle subpath here. So case 3, query ST does not belong to case 3 if and only if E belongs to this middle part, PRST. We use the properties of the R critical case in order to prove several claims. First, we show that if STE is R critical, then the detour part contains more than R edges. To see that, as the replacement path contains at least 3 R edges, and both the prefix and suffix contain less than R edges, and since the replacement path is a concatenation of its prefix, detour, and suffix parts, it follows that the detour contains more than R edges. Second, we claim that if STE is an R critical query, then DSTE equals to the length of the shortest path from S to T in the graph G minus this middle part PRST, which is the distance DST PRST, and we also denote this distance by D tag ST. To see that this claim holds, note that since the prefix and suffix parts contain less than R edges, and the edge E belongs to the middle part PRST, it follows that the replacement path PSTE is also a shortest path in the graph G minus PRST, the middle part. Therefore, its distance DSTE equals to DST PRST. We conclude that we only need to pre-compute these O of n squared distances D tag ST for every pair of vertices S and T in order to answer all our critical queries. And next, we are going to explain how to compute the distance D tag ST. So we want to compute the distance D tag ST. If we somehow knew about an edge E such that STE is an R critical query, then we could have computed D tag ST equals to the minimum over V in B of DSVE plus DVTE. And this would be correct with high probability since the detour contains more than R edges. Then with high probability, there exists a vertex V in B that is on the detour part. And then there's an equality that DSTE equals to the subpath from S to V in the graph G minus C, DSVE, plus the subpath from V to T in the graph G minus C, which is DVTE. The problem is that we don't know for which edge E along the shortest path PST it holds that STE is an R-critical query. And even if we could somehow compute the following loop, that for every pair of vertices S and T, we would have computed D tag ST equals to the minimum over the edges E along the shortest path PST and over the vertices V and B of the length DSVE plus DVTE, where the replacement paths PSVE and PVTE both avoid the middle part PRST. If we could somehow compute this loop, it would still be too expensive and inefficient, as it would take omega of n to the 4 over r time, which is more than cubic. We describe an idea for reducing the runtime of this computation. The first thing we want to do is to find the first common edge of the shortest path PVT and the shortest path PST. And we denote this first common edge as EI. In the paper, we show that EI can be found in O of log n time using a binary search and an LCA data structure on the shortest paths tree, TS. And we use, in order to do so, we use the fact that we assume that shortest paths are unique in G, and therefore it follows that the subpath of PVT from EI to T is the same subpath of PST from EI to T, which is the unique shortest path from EI to T. And this observation is used in order to run the binary search in O of log n time and find this edge EI. So we are given the pair of vertices S and T and the vertex V and B, which is potentially on the detour part. And we want to compute the length of the shortest path from V to T that avoids the entire middle part PRST. Let us enumerate the vertices along PVT as follows. V equals to V0, then V1, V2, up to Vk, which equals to T. So Vk minus R is the vertex before the last R edges of PVT. And the edge EI is the edge from Vi to Vi plus 1. And here's an observation. So we want to compute the length of the shortest path from V to T that avoids the entire middle part PRST. And the observation is that it is sufficient to compute the length of the shortest path from V to T that avoids the entire subpath from Vi to Vk minus R. And this computation can be done completely independent of S and E. So we only look at the shortest path from V to T, and for every index I, for every vertex Vi, we want to compute the length of the shortest path from V to T that avoids the entire subpath of PVT from Vi to Vk minus R. So this is the length of the shortest path from V to T that avoids the entire subpath of PVT from Vi to Vk minus R. And this computation is independent of S and T. It's simply a post-processing of the SSRP algorithm with source vertex V. So we describe how we compute these distances. We build a table TV from the output of the SSRP algorithm with source vertex V. The SSRP algorithm with source vertex V finds replacement paths for edges E along the shortest path from V to T. And we want to keep only a subset of these replacement paths. Which replacement paths we want to keep? Only those that depart from PVT before the last R edges and re-enter the shortest path PVT on its last R edges. So here there are three such replacement paths. One that departs in V2 and re-enters in V15, and its length is 2 for the prefix, 20 for the detour, plus 4 for the suffix. So we had an entry in the table for this replacement path. Here is that entry. And the entry, the first value is the index I tag of the departing vertex, the exit index. So this replacement path departs in V2. So the exit index I tag, the departing vertex, is V2. So we write 2. And the length of this replacement path is 2 for the prefix, 20 for the detour, plus 4 for the suffix. It is 26. And we note that this replacement path that departs in V2 and re-enters in V15 avoids the entire subpath of PVT from VI tag, from V2, up to VK minus R, V14. We also add this replacement path that departs from PVT in V4. So the exit index I tag is 4. And its length is 4 for the prefix, plus 18 for the detour, plus 4 for the suffix. Its length is 26. And we also add this replacement path to the table that departs in V12. So the exit index I tag is 12. The length of this replacement path is 12 for the prefix, 7 for the detour, plus 2 for the suffix. It is 21. And in the paper, we show that if we sort this table in increasing order of the exit index, then the lengths of the replacement paths are sorted in non-increasing order. So next, we explain how to use this table that we build, T of V, in order to compute the distance from V to T that avoids the entire middle part, PRST. So the first thing we do is we find the first common edge EI, as we explained before, between the shortest path PVT and the shortest path PST. So here EI is E6. It's the edge from V6 to V7. This is the first common edge of PVT and PST. The second thing we do is we run a binary search where we want to find the entry in the table with the maximum index I tag, with the maximum departing index that is less or equal to I, to the index of the first common edge. So we want to find the replacement path that departs before EI, before E6, that departs in the last vertex before EI. So it is among the replacement paths in the table. This is the replacement path that departs in V4. Then we find, and then we return its length, 26. So again, we look at the table, we search for the maximum entry that the index I tag is at most I. So we search, we find this entry that I tag equals to 4, which is the maximum index that is at most 6 in the table. And we use the binary search to find this entry in O of log n time. And then we simply return its length, the length of the replacement path that we know that avoids the entire subpath from V4 up to Vk minus R, and in particular, it avoids the subpath from EI to Vk minus R, the entire middle part. And this is the distance that we return. We say that 26 is the length of the shortest path from V to T that avoids the entire middle part. Finally, we outline the analysis of the runtime of the preprocessing algorithm. So if we accumulate all the terms that we had so far, then the runtime is this expression, which is minimized when R and X equal to these terms. And then the preprocessing time is O tilde of n to the power of 2.9953 for omega that equals 2.373. And in the paper, we describe that we can replace the n over R invocations of the SSRP algorithm with a more efficient batch SSRP algorithm, whose runtime is O tilde of m n to the power of omega plus f plus n to the 3 over R. So we replace this n over R times mn omega term with this term, mn to the power of omega plus f plus n to the 3 over R. And then the entire runtime is minimized for omega that equals to 2.373 when R equals to this term and X equals to this term. And then the preprocessing time, it's O tilde of m n to the power of 2.873. So thanks for listening. I hope you enjoyed the presentation, and goodbye.